Hi, I am Seyed Abolfazl, Javadein, and welcome to this video and welcome to this channel. This is the third video about optimization in the machine learning and neural network and deep learning. I am very sorry for a big late and big delay from to creating this video from the previous video second video. As you can remember, in the previous videos we covered I created two videos before, and we covered the necessity of having a good gradient descent. We covered momentum gradient descent. We covered nesterov momentum gradient descent, and at the end of the previous video we got to a conclusion. We got a conclusion that having a good suitable learning rate is necessary to cover and to reach the global minima in the loss function. And learning rate, having a good learning rate is not an easy task. For example, if a learning rate is too small, it takes a long time to get the global minimum. And if the learning rate is large, you can't get the global minimum. It may be exploded, or it can't converge to the global minimum. If you can't remember this concept, please see the previous videos. I think that was useful for you. And at the end of the previous video, we reached to a question. We got a question that, is there any way to have a customized learning rate for each weight in the neural network and deep learning? This is the concept that we want to answer in this video. And in this video, I want to cover AdaGrad, I want to cover AdaDelta, RMSProp, and Ada. Some useful and some very popular optimizations in neural networks. Okay, we start the video. And as you can see here, we start from AdaGrad, adaptive gradient. The idea behind the AdaGrad or adaptive gradient is that each weight in the neural network can have its spatial learning rate. For example, if we have this layer with some neurons and another layers with these neurons, okay, and we connect these weights together I connect these neurons together with some weights. You can see here, and for example, connect some neurons, these neurons together with some weights. The idea behind the AdaGrad is that I want to have a different learning rate for this and, for example, this weight, for these two weights, the W and W2. For example, the learning rate of this W1 is alpha 1, and the learning rate of this another W2 is alpha 2. In AdaGrad, we learn how you can have a customized learning rate for each weight. Amazing. Okay. The math behind this idea is very simple. In the math behind this idea, we create something we call RT here. You can see here, RT. And I can write, okay, with change the color. You can see here we have RT. RT is sum of the squares of gradients of the change of the weights. For example, in the when we are this is the change of the weights in the in previous steps. For example, if we are in this, I want to put, okay, I go from this step to this step. We changed some weights here. This is the idea that you can see here. You can see that here. Change the new weights. This is the changing weights. The how much the weights from the previous the next previous step change to this step, and this is something that we have that in a vanilla gradient descent here. This you can see here. This is something that we have in the vanilla, okay, in the vanilla gradient descent. We have this change of the weights, and okay, and we use this change of the weights to create make a score of them and sum the change of the weights and create this RT, and we put this in the RT in this formula to create new weight. For example, my previous weights here was my previous weight from here was this, and here my previous weights is this, which we have a change here in the weights, in the weights from the previous step to this step. But what is alpha? Alpha is our default learning rate, the learning rate that we have in gradient descent until now. You can see here this learning rate. This learning alpha is this alpha. Okay. Okay, we have alpha or learning rate that we had in vanilla gradient descent, and we have change weights that we had in vanilla gradient descent. Something that's added in the adaptive gradient is this formula and this amount. Okay, what does this mean? This means that in the if, okay, this means that if we have a big RT, if we have the big RT, if RT is large, is very large, this division will be very small, because the RT here, large RT, make this division small. Okay, but in opposite, if we have a small RT, I change this small RT, makes this division very large. Okay, what does this mean? This means that if we have a large RT, this RT is the sum of a score of changes. If we have a large RT here, this score will be small, and means that the previous weights will go in a little have a small change here. Okay, this means that we have a small change in the weight. But when RT this is small, this division would get large, and the old weight will lose a large portion of it, and this will lead to a big change, large change. Okay, that's very easy. What does this mean? This means that if at the first step here, the RT at the first step RT is 0, and at the second step RT for step 1 is R1. This is for step 0. R0 is 0 for step 1. R1 is R0 plus the score of changes. Okay, I can write that in this is, and for step 1, R1 will be R0 plus the square of changes in weight. And what does this mean? This means, for example, in the first step, we have a small r1. Why? Because we have only r1 is have a change in weight plus rt. But what is r2? R2 will be R1 plus changes in the weight. What does this mean? This means that R1 is dependent to R0 and RT. It depends to RT minus 1. It depends, and RT minus 1 depends to RT minus 2, and RT minus 2 depends to RT minus 3, and we'll go to R0 means that's 0. And you can see here RT is RT minus 1 plus the square of changes. I want to show in the, I think if I create another blank page is better. Okay, it means that RT is dependent to RT minus 1 plus amount of changes in RT, and this means RT minus 2 plus changes in RT minus, and this means RT, this is from RT minus 3 plus the square of changes in T minus 2. And as you can see here, if we go from, and this will have go to R0, that's this is 0, and R1 is R0, that's 0 plus the square of changes. And what does this mean? This means that when we go from R0 to RT, if we go in the next steps, we go forward to reach the global minimum, the amount of RT will go larger. But here amount of RT is very small. Here we have going in this direction, we have amount of RTs go larger. Okay, according to this, from this formula, I make this slide cleaner. Okay, from this formula, you can see here that in the first steps we have little RT, means that RT in the first step RT is very small, and means that we have a large change. Okay, in the first steps of loss function, we will want to move to the global minimum with large steps. For example, here this is a loss function. If this is a loss function, in the first steps we go from here to here, big in the first steps we go from here to here with big steps. But when we move forward to the global minimum, and we get closer to the global minimum, all steps will be smaller. Why? Because RT will be larger, and large RT makes small changes, means that in the last steps that we are close to the global minimum, we have here short steps to reach the global minimum, and this is an amazing idea. You can go with long movement, with long steps, go to the global minimum, and after some steps, when we get closer to the global minimum, we make shorter steps to reach the global minimum. And these shorter steps help us to reach global minimum and to converge the global minimum. But this is the idea behind AdaGrad. But the idea is simple and very effective. But there is a problem here. That's what is the problem. The problem here is that, and okay, I explain this delta here. Here, okay, this is an amazing color. I explain this here. This is, we know that this is learning rate. We know what is this and why this is. This is for numeric stability. You can see here stability. In the, you can see here some words with the numeric sometimes this word numeric stability in the papers. This numeric stability, what does this mean? This means that, for example, if in some steps this is very art is very less and very small, and art is very small, this here this portion of the division will be 0 for when art is very small, will be 0, and the 0 in the division make the 0 in this division make problem for us. And here this is our division. Sometimes you can see this art is very close is 0 or very, for example, the first step in R0 in the R0 you can see here, or R0 is 0, and this can create problem for us. For example, in the first step 0 we have alpha divided by we have alpha divided by 0, and this is not suitable for us. We don't want to get this. We use this delta. Delta is something very small number used for stability and numeric stability. What does this mean? This means that it is something very close to 0. For example, 10 to the power of minus 12 or 10 to the power of minus 20. Something very close to 0 that will help us, that we don't have division by 0. We don't have division by 0. This is something a very small number. For example, 10 to the power of minus 12, 10 to the power of minus 20. That can help us to calculate or division, and we don't have division by 0. Okay, this is a very good idea in AdaGrad, adaptive gradient. And okay, but there is a problem for adaptive gradient. Adaptive gradient, for example, you can hear something that we can see here in the adaptive gradient is that if we go forward to the global minimum, and you can see here that this, when we go forward to the global minimum and we go closer and closer to the global minimum, RT will be larger. RT will be larger and larger. And when RT is larger and larger, this division that I write it again here, this division will be shorter and shorter. And after sometimes you can see here we have a very short division here, a very short number here. What does this mean? This means that in this formula, I write this formula here. This means that in this formula. Okay, this formula I write it. Okay, this formula. When we go closer to the global minimum, this RT will be larger, and larger RT means that this division will be smaller. And the smaller division, what does this mean? This means that, for example, we have in the when we are very close to the global minimum, we get this minus something very little number here. For example, this number here, and multiple times amount of change. Why does this mean? This means that when we go, and this is a very low, this means that in the when we go forward after many steps, we have a very small changes in the steps, and we have very small steps, very tiny steps, and this will lead to vanishing gradient because we don't have a much amount of change to the global minimum. And this is the problem of AdaGrad. And RMSProp is the idea that help us to solve the problem. RMSProp is stands for root mean square propagation, and it is it's a suggestion from Geoffrey Hinton. You can see here RMSProp is an unpublished adaptive learning rating optimization algorithm. First proposed was Geoffrey Hinton in lecture sheet of his online class. This is an idea of Geoffrey Hinton, but not published as a paper. And this is something that he said in slides in his classes. Okay, he said that we can use something rho, for example, here, and rho is something between 0 to 1, and make a balance between these two, between this and this, RT minus 1 and this square of changes. And that will help us to don't have a vanishing gradient here. For example, and we can use this idea to escape from vanishing gradient. Okay, what does this mean? Well, we have a variable with and constant variable rho, and that is something cost, and Hinton suggested it be this 0 or 9, and this will create a balance between these two sentences in RT, and that help us to, for example, when in the first steps, for example, R1 is according to something that Geoffrey Hinton suggests, rho 0 or 9, RT R0 plus this will be 0 1 delta, okay, delta square 2. Okay, here in the first steps, in the R1 is 0, R0 is 0, R1 will be this is 0, and this will be R1. And for R2 means that, for example, 9 0 9 plus this one, this. And you can see here R2 depend on R1 and R1 depend on R2, and after some steps we can see here that there is a balance between these two sequences, and we don't let RT in each steps. We don't let RT get higher value. Because of that, we times that to something closer to 1. And after that, we make article a little smaller, and this can help us to escape from the problem in the AdaGrad, vanishing gradient. At the times that Geoffrey Hinton was thinking about the idea about RMSProp, another scientist developed an idea close, very similar to Geoffrey Hinton's, with the name of AdaDelta. And this is AdaDelta. This is AdaDelta. Another this is AdaDelta. Okay, another scientist has a thinking about this problem and create something AdaDelta. AdaDelta is very close in the concept to the RMSProp. The only problem is that AdaDelta removes, the only difference is that AdaDelta removes learning rate entirely and replace it by the root mean square error of parameters up to date. And this is the paper that Sebastian Roeder suggests AdaDelta. Concept is very close to the RMSProp. The only difference is that AdaDelta removes the learning rate entirely and replaces but the root mean square error of the parameters. You can see here. This is AdaDelta and this is RMSProp. For this formula is very close to each other, and this is another formula that we covered in until now. This is from previous videos, this is from previous video, and this is this video. I covered this in this video. Okay, and the next amazing optimization concept is Ada. Think about situation that you can have all the good things together, momentum and row that was this row that was proposed from Geoffrey Hinton. You can have a situation that you have the idea, momentum from momentum SGD, and row from RMSProp. This is the idea behind Ada. Okay, I explain this to you. Adam is very easy in the mathematical concept. You can see here that we have these two formula here. This is the formula is not something that we want. We see this first time. This is the RMSProp formula. I change. This is RMSProp formula. You can see here this, and we have this in Ada here. Okay, and this is the formula from momentum, and we want to use all of this formula to create a Adam concept. Okay. Okay. To use Adam concept, we get best from these two concepts, momentum and RMSProp. What does this formula mean? We have, okay, we change the weights according to this formula, and this formula okay. I have my camera get off, and I have stopped to open the camera again, to turn it off again. Okay, we have these two formulas, and this is the main formula. This concept here is from momentum, and this is the concept here comes from RMSProp. Okay, I explained what this is and why this is suitable for us. At the first steps, what we have at the first steps? At the first steps, we have, for example, we have we create S0 and R0 in the first steps. This R0 is from RMSProp, and this is from nesterov momentum. And at the here, what we have at the first steps, S0 tilde is S0 divided by something alpha 1 at the first steps, and RT tilde RT divide by this again here. Okay, what does this mean? This means that at the first step, what we want to know is that we know from Jeffrey Hinton's suggestion that alpha is 0 or 9. Okay, but what does this mean? This means that here at the first steps we have in the dominator we have the first step 1 minus 0 or 9 to the power of t. T is for step 1 is 1, and this means that at the first steps the dominator is here 0 or 1. What does this mean? This means that at the first steps S0 tilde is 10, because this will be S0 divided by 0 or 1. This means 10 folds of S0. Make longer steps at steps 1, at the first steps, so longer steps to go forward to reach the global minimum. And RT tilde is like this again. It means that, for example, here if we have here our loss function at the first step S tilde 1 is 10-fold S1, and means that we have a very long steps to reach the global minimum. We have S1 tilde 10-fold S1 and T1 tilde 10-fold T1. Amazing. But at the next steps, what we have here? At the next steps, okay? At the next steps, what we have here, formula is this: S tilde T ST divided by 1 0 to the power of T. Okay. At this second steps. What we have at the second steps? At the second steps, this will be 1 minus 0.09 to the power of 2. Okay, means S2 tilde. This is 2. S2 tilde is S2 and with this denominator. And what does that mean? That means that we have a, in the S2 we have a shorter steps, and S3 will be what? S3 tilde. We have S3 minus here. What does this will be if we use calculator? Means that will be S3 minus this amount. Okay. Okay. What does this mean? We can see here that at the first steps we have we go to the global minimum with long steps, and after that here in the first steps here we have this amount 0.09. Here we have a larger denominator, means a smaller this S2 tilde, a smaller S2 tilde, and here we have again a larger denominator according to this, and we have a smaller S3 tilde. Means that if we go forward, our steps will be smaller to reach to the global minima. And this is the concept behind the Ada. And you can see here we have in Ada we have all the good things together. We have momentum. Use the idea of momentum here because, and we can have that to have a faster reaching to the global minimum. And we use the idea of RMSProp rho here. We can use that to reach to the global minimum fast, and with the effect of vanishing gradient, with the less probability of vanishing gradient, Okay, this was the third video. If you think these videos are useful for you, please subscribe to my channel. And I want to create some real world projects. I want to develop some real world projects in some videos. Don't forget to subscribe. Have a nice time. Bye bye.